Okay, we'll start with today's class.
Okay.
So today we'll see some problems on heat exchangers. I'll just briefly tell what has been taught in the class. Firstly, you know the types of heat exchangers: shell and tube, double pipe, plate heat exchangers, and in double pipe also there are parallel flow, there is co-current, and counter flow. Parallel flow means there are the fluids are they are traveling in the same direction. That inlet of both the fluids are on the same side, and the outlet are on the same side. For counterflow is the opposite. Suppose one is coming from on top, and another fluid is coming from bottom. So that is the counterflow. Then there are compact heat exchangers. That means there are cross flow type. I mean, they may be perpendicular to each other, something like that. And then there are shell and tube heat exchangers that can be one shell pass, different combination of number of shell passes and number of tubes passes. So one shell pass, two tube pass, one shell pass, four tube pass. So there are many different combinations of shell and tube depending on your requirement. So mainly designing of heat exchanger has been taught. So you might have another course later, maybe in your during your engineering course, design heat exchanger design engineering, something like that. So that will also take care of such. Mainly today what we will discuss, that these are also very important part of that course. Okay, so first thing is, for since in all this heat exchanger there are two fluids required, one cold, one hot. So um, there are two different types of tubes, you can say tubes, one is tube, one is shell, or there are two different, then it may be concentric also. So the total what is that called, resistance, for calculating such, suppose for concentric tubes, concentric cylinders, the total resistance can be calculated by, this is we have already done in the conduction part also. So this is the total resistance, suppose 1 by ui ai. It can be also written as 1 by u naught a naught. That means the inside, this is according to the, based on the inside tube, and this is based on the outside tube. So this is equal, and this can be given by 1 by hiai plus r of wall. Here the resistance due to conduction will also come. If we consider the resistance of the wall, then 1 by h naught a naught. So sometimes you may consider it, or sometimes you may not, depending on the question. One question sir has done in the lecture, that there he did not consider this R wall, resistance of the wall. So this can be written as, the resistance is only this. So we can multiply with, suppose if you want to calculate with respect to the inner tube, we can write it as, if we multiply ai throughout the whole equation, we can get like this. R wall. So for concentric cylinder, this one will be, resistance will be ln r naught by ri 2 pi kl. This length is the L is the length of the cylinder, okay? And this is AI by H naught A naught. Yeah. So this AI will get cancelled. So the total, this is the total resistance. Okay, so this is the R wall. This whole one is the R wall. You have to multiply with AI because since I have multiplied AI throughout the whole equation, AI can be written as 2 pi RL or pi d, simply pi dl also you can write 2 pi KL. So 2 pi L gets cancelled plus AI is 2 pi RL H naught. This is RI, this is R naught, RI, and this is R naught. So you get only 1 by HI. This is RI ln R naught by RI divided by K plus RI H naught into R naught. So this ratio of R naught and Ri you can convert in terms of D or in diameter also. R naught by Ri will be D naught by Di and Ri by R naught will be Di by D naught. And in place of this R we can write Di by 2. So whatever is given in terms of Ri or Di R or D you can write this equation. The next is you have to sometimes we don't know we cannot define the temperature difference since they are not uniform throughout the whole heat exchanger. So in that case we have to consider the delta Ts delta T LMTD, the log mean temperature difference. So this LMTD is given by delta T1 minus delta T2 divided by Lm delta T1 by delta T2. So delta T1 and delta T2 is this is the length of the heat exchanger. This is the temperature. So if for parallel flow it will be like this. The hot fluid has a higher temperature. The inner in the entrance of the hot fluid is higher and TH naught will be lower of course, and the cold fluid will have lower temperature and it will extract heat from the hot fluid, so the outlet temperature of cold fluid will increase. So here delta T1 will be this and delta T2 will be this or any one. This may be delta T1 and this may be delta T2. That sign will take care of since here also there is this ln is also there. So anyway, one side delta T and another side delta T is the delta 1 and delta 2. And for counter flow, the inlet of hot temperature is hot fluid is obviously high, and since it will lose heat, so the outlet of this hot fluid will be lower, and the inside of the since the direction is opposite, so the TCI will be here. This is for counter flow, this is for parallel flow. This is the direction of fluid flow of the fluid. This is the direction of hot fluid. This is the direction of cold fluid. So it will gain heat. So the temperature will rise. Sorry, this is O. So here delta T1 will be either this. If delta T1 is this, then delta T2 should be this. If delta T1 is this, then delta T2 should be this. Any side. But you have to consider only one side as delta T1, another side, just the opposite side as delta T2. Okay. Then we have, okay, for the same fixed temperature and fixed heat transfer rate, area required by this counter flow is always lesser than the area required by parallel flow, because this counter flow always have higher thermal efficiency more than this parallel flow, because they maintain almost uniform temperature, not always, but they almost maintain uniform temperature compared to this parallel flow. Okay. Then we have, for condensation and for boiling, you know the graph. For condensation, the temperature of hot fluid remains constant, because for condensation, the latent heat, the sensible heat does not change, only the latent heat, right? So that latent heat is used to Tci and Tc naught. This takes up the latent heat and then it increases the cold fluid temperature. The cold fluid takes up the latent heat and then increases. So this is the condensing fluid. That hot fluid, that is the condensing fluid, and that condenses. It just changes the phase. It does not change the temperature. So that hot fluid is the condensing fluid. And then for boiling, for boiling, the temperature of the cold fluid remains constant, Tc. This fluid is the boiling fluid. This is Thi, this is Th naught. Because this fluid, it gains energy, it gains heat from the hot fluid and it starts boiling, and that it does not change the temperature of the fluid, but then it changes the phase of the fluid, so that fluid is boiling. And then we have, okay, so there is one case where we don't use the LMTD, and that case is in case of this counter flow. There is one special case of counter flow where the temperature difference is exactly the same. It is maintained the same everywhere, all throughout the length of the heat exchanger. It maintains exactly the same temperature difference. That means this graph will be exactly parallel to each other. Then there is no difference. I mean, it will become 0 by 0. So in that case, we will simply use delta T. So anyways, we have a constant delta T there. So the uh, temperature difference considered in that case will be simply delta T, the temperature difference between the this graph. Okay. Then for shell and tube heat exchanger, we have for shell and tube heat exchanger, we have this formula for delta T LMTTS F some fraction into LMTD for counter flow. So this is the equivalent counter flow with same temperature, and same area. So this is for shell and tube. So if we consider suppose, because since this shell and tube is a bit complicated, so we can directly calculate from the LMTD of counter flow, considering that they have the same temperature, I mean inlet outlet temperatures, and the same area, heat exchanger area. So we can find out this. Then we have many different factors like P, there is thermal efficiency. Thermal efficiency, we have TSI minus TTI. So this is the inlet temperature of shell side fluid, and this is the inlet temperature tube side fluid. And then we have relative thermal capacity, and there is a relation between this and F also. F is the F is written as it's the correction factor, and this is the maximum delta T which can be attained by the shell and tube. And since it is a fraction, so it varies from 0 to 1. Now this relative thermal capacity is equal to shell side difference and tube side difference. It may be cold, it may be hot. I mean, the shell side fluid may be cold, it may be hot, but the sign will just take care of that. So this is just the difference. The numerator is just the difference between the shell side tube temperatures, and denominator is the difference between the tube side temperatures. And then we have this effectiveness NTU method. And since if we continue to find out the this heat capacity, I mean sorry, this just 1 minute. हेलो. हाँ. हाँ दादा, आप CFN में हो ना? हाँ, आप सिक्योरिटी में दे दीजिए. OTP चाहिए. 587113. हाँ हाँ, थैंक यू. Yeah, so this can also be written as MCP tube side and MCP heat capacity at the shell side of the shell side fluid. Okay, then so if you don't want, I mean this, if you go with this LMTD method to find out the temperature or to find out the area required for the heat exchanger, so that may be cumbersome because that is it follows a uh, iterative method. You have to keep on changing the one because sometimes their two temperatures might not be known. So for that one you have to assume and another you have to find out from that, and it may take a long time. So for that this NTU method was proposed here. So this effectiveness is given by effectiveness of the heat exchanger is given by Q by Q max. So we'll be using all this formula today in today's class. Delta T, and this Q max we get by MCP minimum.
Ma'am,
Yes.
ma'am,
Yeah, yeah, tell me.
those parameters are considering while designing any heat exchanger for any process.
Yes, yes. So actually this, that is what I was telling. You might have a course on this designing. So for that you have to use all this. Simply you cannot, if you go in industries, I mean, for designing this heat exchangers and all, you have to see how much is the effectiveness and how much maximum you can extract from from an equipment. So for that, this is for heat transfer. Maybe for mass transfer also you'll have for so many things. So you have to, according to the purpose, according to what is required, what will be the requirement, you have to design the heat exchanger in such a way. Sometimes you might, obviously area you would like to minimize because that will minimize the cost and all. So you have to consider all these design parameters. Okay, then we have this Q max is given by this delta T max and minimum of the MCP, whichever fluid has the minimum heat capacity. Then then for it's already there in the notes. Okay, if the MCP of the hot fluid is larger than the MCP of the cold fluid, then this Q will be given by MCP of the cold fluid, uh, in terms of the cold fluid only, this Q. And if the MCP of cold fluid is larger than the MCP of the hot fluid, then this Q will be defined in terms of the hot fluid. So it is there in the in your lecture notes you might see. Then we have, okay, this effectiveness for different parallel flow. Effectiveness is given by 1 minus exponential minus NTU 1 plus CR divided by 1 plus CR for counterflow. From your interview point of view, you might, this shell and tube might be very, I mean, this whole of the heat exchanger part might be important. because in industries directly you'll use this only. So this CR is capacity ratio, means the ratio between the capacities of the minimum heat capacity and maximum heat capacity. For shell and tube, it is very big. So in class, I think this one was given inside here. So please check this. I mean, this minus 1 to the power of minus 1 is here or here. I think it is here. Okay. So we'll start with the questions. So first question is, consider a concentric tube heat exchanger with an area of 45 meters square operating under the following conditions. So they have just given um, for hot fluid and cold fluid, they have given heat capacities. They have given inlet of both and outlet of only cold fluid. But they don't have for that is what they have asked. What is the outlet temperature of the hot fluid? So this is simple. Just by doing the energy balance, you will get this. Energy balance is MCP of hot fluid THI minus TH naught is equal to MCP of cold fluid. For cold fluid, it is C TC naught minus TCI, because for cold fluid, outlet temperature is higher than inlet temperature. So the heat capacity rate they have given is this MCP. Directly you can write this. So for hot fluid is 6.2 kilowatt per hour. This side also kilowatt per hour. So anyways, you don't need to convert them into the SI unit. Then H 70 degree minus TH naught is equal to 3.2 into 60 minus 25, right? So calculate this TH naught. This is a simple question. Calculate this TH naught. How much do you get?
52.52 degrees Celsius.
Yeah, this was an easy one. Just do the energy balance and you'll get. Now next is aluminum tubes thermal conductivity they have given of inner and outer diameter. Um, Measurement is given. Di inner diameter is 11 millimeter, outer is 13 millimeter. Are used in condenser of a refrigeration system. Under normal operating conditions, convection coefficient of HI equal to 5000 watt per meter square Kelvin is associated with condensation of the inner surface of the tubes, while a convection coefficient of H naught is equal to this is maintained by natural convection of the outer surface. What is the overall heat transfer coefficient based on the inner surface? If the tubes are unfinned, consider the tubes to be of unit length for the calculation. So L is simply 1. This is simply a resistance problem. They have asked to find out the overall heat transfer coefficient based on the inner surface Ui. So what we have done there, this is exactly what they have asked, this one. Okay. So if they have asked in terms of the outer fluid or outer diameter, you have to calculate U naught just like this, 1 by U naught. Then after you get 1 by U naught, just calculate U naught. But now for this question, you have to use Ui based on the inner surface Ui. So 1 by Ui is equal to 1 by Hi plus Ri ln R naught by Ri divided by K, sorry, plus this is Ri. So you can write in terms of D also. Instead of Ri, you can write Di by 2, then ln D naught by Di divided by K plus Di D naught into H naught. So please calculate this. You have to find out Ui.
Ma'am, overall diameter will be considered here, or radius. Radius will be considered or diameter overall considered.
Anything you can consider, na. In
Okay.
ter in terms of Ri, you can write Di. In terms of R naught, you can write D naught. That's what I said. You can write either in this form or this form. In terms of radius, you can write this. In terms of diameter, you can write this. Since diameter is given, you can use this. Since this inside ln, it is a ratio of both the diameters. You may write directly 13 by 11. You may not write 10 into 10 to the power minus 3 because that will anyways get cancelled. So here also there is ratio. So this is very advantageous for your calculation. Wherever you find this ratio, you can directly, you may not waste time by writing 10 to the power minus 3.
0.084. Sorry.
So you have to find out ui, not 1 by ui. They have asked to find out the overall heat transfer coefficient, not the resistance. So you have to find out ui just to
Okay.
one.
Option A.
Yeah. Okay, next. This is a problem of shell and tube exchanger. A shell and tube exchanger, two shells, four tube passes, is used to heat 7500 kg per hour of pressurized water from 28 to 96 degrees Celsius with, with 4000 kg per hour pressurized water entering the exchanger at 240 degrees Celsius. So this heat exchanger is used to heat this water. That means this is the cold water. I mean the cold fluid. So the this is, since it is kg per hour, so it is the mass flow rate. Okay, mass flow rate of the cold fluid is 7500 kg per hour from 28 to 96. So by seeing the temperature also you can guess that it is, since it has gone from small to higher temperature, so it is getting heated up, so it is a cold fluid. So the inlet of this cold fluid is 28 degrees Celsius, outlet is 96 degrees Celsius. Then next they have given this is heated with the help of this water. That means this is the hot fluid and its mass flow rate is 4000 kg per hour entering the heat exchanger at 240 degrees Celsius. Entering, that means the inlet HPHI is 240 degrees Celsius. Outlet temperature is not given for the hot fluid. If the overall heat transfer coefficient is 1500, that means U is equal to 1500 watt per meter square Kelvin. Determine the required heat exchanger area. F is given as, that correction factor is given as 0.97. So we have seen that for shell and tube heat exchanger, delta T LMTD is equal to F into, this is for shell and tube, F into delta T LMTD for counterflow. So directly we can calculate this. Now how do we get A? A is nothing but Q is equal to UA delta T LMTD, right? But this is for shell and tube. So if we know the, we already know U, we have to calculate this delta delta T LMTD from here, and Q you can calculate from here, right? Either here or here, anything. So Q is also equal to mCp delta T for cold, that is also equal to mCp delta T for hot fluid. So since hot fluid temperature, outlet temperature is not given, you can calculate from the cold fluid also. It is the same thing. So this is for LMTD, and for calculating Q, it will be mCp for cold fluid into delta T. Delta T is Tc naught minus Tci. So just calculate this Q and delta T. U is already given. You can calculate A.
Q is 510000. 51 double 4 times 0.
Okay, now calculate delta T LMTD for shell and tube.
Ma'am, temperature of outside hot for outside. We required calculate Q for uh, outside of the
Yeah, yeah,
other.
outside of hot fluid, right? Outlet temperature
Yes,
of hot fluid.
yeah, yes, yes,
So
yes.
how will you
So
cal?
we consider this Q equals to MCP delta T. So delta T I is given, MCP we know, Q know. So we will put in the equation, we will only calculate delta THO. So T, like this equation given here, Q is equal to MCP delta
Yes,
T.
yes, yes. But
So
that MCP should be off for hot fluid.
hot fluid, yes.
Huh. So,
So we have given that all quantities. Just put in an
huh, huh,
equation.
huh. So
We get it.
calculate that.
THO we get directly.
Huh. So how much you get THO?
Ma'am, I did not
Yeah, yeah.
calculate. I just have idea.
Okay, okay. Calculate that. Yeah, that is right. That is right. You're correct. But I think what did you take for cold fluid? Mass flow rate for cold fluid.
7,500.
Okay, here one thing is there that this hour is not an SI unit. Instead of hour, it should be second. Second is SI unit, okay?
Yes.
You have to take care of this units.
So we convert into second.
Yes, yes. Convert per unit second, per second, kg per second. So just divide this 7,500 by 3600. While equating, there is not much problem, but if you find this Q, that time it should be taken care of. While equating, just like this, for both the M divide by 3600 will come, so that will anyways get cancelled. But while finding out Q, that is important. You have to,
Ma'am, 1416. The value change after conversion of hours to second. Q is change.
Q is how
One
much?
1416.66 after converting the hour to second.
I am getting different answer.
How much, ma'am?
5.93 into 10 to the power 5.
Wait, ma'am, I will check. It's mistake.
So did you get the CP value? CP value is given here. This is for cold fluid, and CP value for out for hot fluid is this. This you don't need to convert anything because it is anyways joule, kg, Kelvin, all are SI unit. If it was kilojoule, then you should have convert into joule, but it's already in joule.
Ma'am, CP value is CP value. First line. For hot water, what is the CP value?
For
For
hot water,
what?
it is this. So here you have to see very carefully while reading the question. This is both are for water. Okay, they have given the CP values for both because both the fluids used here is water. Just one is cold water, another one is hot water. So how will you identify between these two?
Yes, yes, ma'am. I get the answer. 59330 something 10 raised to 5.
Yes, 5.9 you should get.
Yes.
Yeah.
I have remaining the multiple of the CP value in this equation. MCP. I just take a mass flow rate. Take
Okay,
in this
okay. You have
equation.
missed the CP value. Okay.
Yes.
So did you get how to find this? The first one is the above one is for cold fluid, this one, because the temperature here is lesser and the temperature here is higher. The below fluid, it is higher. That's why this is the hot fluid and this is the cold fluid. And what temperature is this? This also you might ask. This is exactly the average temperature of the cold fluid, average temperature of the hot fluid. So if you cold fluid is 28 to 96, it goes. So just do average of that. 28 plus 96 divided by 2 and you convert into Kelvin, you get this. Similarly, when you find out the hot fluid, you will get this. Anyways, just by looking at the temperatures, the one which is lower, that is for cold fluid, and one which is higher, because in this question both are water. In some questions it may be water and oil also. So there you might differentiate easily. But here both are water. But so which one is for cold, which one is for hot, that you have to identify just by looking at this, at what temperature this CP is given. All right. Okay, I'm just writing directly. The temperature of or outer outlet of hot fluid is this 118.7 degrees Celsius. You should get this. Then delta T LMTD for shell and tube is F into delta T LMTD for counter flow. And in counter flow, what was the condition that all the temperatures have to be same? Now you got all the temperatures. So for counter flow, that will
Ma'am,
be the
here is a mistake. 3600 divided here for converting while hour to second in this equation.
yeah. What I didn't get.
So answer is to be 2 to 7.87 Celsius.
Why? I mean the answer should be this. I mean you are telling for TH not.
Yes, yes, yes.
You are asking me why this is why
No,
have
no, ma'am. There is a 360. There is a 1 0 is extra.
it should be 3600 no hour to
Oh,
second 60 into 60.
I again done the mistake same previous question. Sorry, ma'am.
Okay, you calculate it later. I have given you the this
Okay,
should be the answer for Q and this should be the answer for TH not.
okay.
Now I'm directly writing so for delta TLMTD for shell and tube is equal to F into delta TLMTD for counterflow provided all the temperatures are of that of the same as shell and tube. Okay. So we can consider these outlet and inlet temperatures for counterflow also. So this is F is given as correction factor is given as 0.97 0.97 into delta T1 minus delta T2 divided by ln delta T1 divided by delta T2. So for counterflow it is uh, H naught minus here if I draw counterflow, it is not always this is exactly parallel, but it's not always parallel. It can be like this also. It can be like this also. Anyways, this is THI, this is TH naught, this is TCI, this is TC naught. So for counterflow, delta T1 is THI minus TC naught, delta T2 is TH naught minus TCI. Okay, so this is the one which will follow. TH naught minus TCI is this minus 28 minus TH naught minus sorry THI minus TC naught 240 minus 96. Did you get how I have done how I have taken this delta T1 delta T2?
Yes, ma'am.
Yeah. So you calculate after you calculate this you should get this as we should get this as 111.9 degrees Celsius. This for shell and tube. LMTD for shell and tube. Now you directly calculate what is this A. A is Q divided by U delta T LMTD So Q you have 5.93 into 10 to the power 5. U you have this 1500, and delta T LMTD is this. So if you substitute all this, you will get area as 3.53. Just calculate all this after the class is over. Then you should just note down all these values. The answer should be this third, last one.
Yes, get it.
Okay,
1.9.
okay. Calculate this area also later. Should we move to the next question?
Yes.
Okay, next is a counter flow concentric tube heat exchanger. So this time it is simply counter flow, not they have not said it is shell and tube or not. So this is used for engine cooling, has been in service for an extended period of time. The heat transfer surface area for the exchanger is 5 meters square, and the design value of the overall convection coefficient is 38 watt per meter square Kelvin. During a test run, engine oil flowing at 0.1 kg per second is cooled from this to this. So this is hot fluid, okay? Since it is cooled, so it is hot fluid. So m dot h is equal to 0.1 kg per second. Here you don't need to convert since it is already second given, okay? 0.1 kg per second. It is cooled from 110, that is TCI is equal to 110 degrees Celsius. Sorry, this is TH, no? TH naught is 66 degrees Celsius. By water, it is cooled by water. That means water is the cold fluid. So supplied at temperature of 25 degrees Celsius. Since it is supplied, it is TCI, inlet of cold fluid, that is 25 degrees Celsius. And we don't know what is the TC naught. We don't know that. And flow rate of water is given as m dot c is given as 0.2 kg per second. Okay, determine whether fouling has occurred during the service period. So for design point of view, this is also one of the factor, okay, which you have to consider since these equipments have been in use for a very long time. There might be some fouling issues also associated with that equipment. So this fouling factor is calculated by RF is equal to 1 minus U actual minus 1 minus 1 by U design. So this is the actual heat transfer coefficient, and this is the design heat transfer coefficient. So RF is found out by that. So they have asked exactly to find out this RF. Note this uh, formula also. Now can you calculate this? You know how to calculate this U from the previous U is already given. Okay, the one which is given is a design value. Design value of the overall convection coefficient is 38. That means U design is given. You have to calculate U actual to calculate this RF. So will you be able to calculate U actual?
Yes, yes, ma'am.
How will you calculate?
By using the formula of Q equal to Q equals to
Yes,
this.
yes. Since area is also given,
Yes,
okay.
just
Yeah, calculate. Just the thing here is that it is directly counter flow it is given. So directly you have to find out delta T LMTD. You don't have to multiply with the correction factor since it is not shell and tube. Okay. So directly you calculate delta T LMTD, and from there you calculate this uh, U. Q divided by A delta T LMTD. Q is
Please show the plus side CP for cold fluid. Okay.
here they have given for both water, but one is water, one is oil. They have given during a
Okay.
test run engine oil flowing at this. So here, anyways, this is for hot one, this is for cold one. TH is given and another is TC. Please calculate this. I'm just coming in 2 minutes. Let me know which is the answer from here. You found out
TCO is 13.5 mm.
U.
TCO, outer
TCO.
cold
Okay.
temperature,
TCO.
13.5 mm.
No, I got something else. Wait. This is 1, this is 2. No, it is 36.4.
Yes, ma'am. This is correct. I have done mistake here. I have minus TCI minus TCU. So the equation will be wrong.
You have to, for
I,
cold fluid, TCO is always greater than TCI because it will take the hot heat now. So
yes.
this you should take care. This for hot fluid THI minus TH naught, for cold TC naught minus TCI. Anyways, whatever numbers you get, if you have taken TCI minus TC naught, then that will be very big. I mean, what was the previous answer you told for TC naught? Hello?
Previous, whatever I was equation take, TCI minus TCU. At that time I got value 13.59. But when I changed the equation, I got 36.4. So
Okay.
only this mistake will be done by me.
Okay, okay. Hmm. So Q you can calculate from any of this, either MCP delta T from hot or MCP delta T from cold fluid. Any of this, if you calculate, you,
Q is 9530.4.
yeah, yeah, right. And A is 5 delta T LMTD is, Did you get delta T, log mean temperature difference? It is exactly the same formula which I have used in the previous question.
$55.7 delta ALT.
Yes, 55.6 or 55.7, whatever. So just if you insert here, you get U actual as, I'm directly writing the answer, okay? 34.3 watt per meter square Kelvin. If you, whenever you have confusion how to calculate this delta LMTD, just directly draw it. Where if you directly draw it, then you can easily find out just this is delta T1, this is delta T2, or this is delta T2, sorry, delta T1, this is delta T, anyway. So that will become very easy. If we, whether it is for counter or parallel flow, just directly draw the this plot of temperature versus the length. Okay, you get this U actual as this, and U design was 38 watt per meter square Kelvin. So now you can calculate what is RF. So RF is equal to 1 by 34.3 plus 1 by 38. You'll get something. This is not plus, this is minus. So this is 29 point, sorry, 2.9 into 10 power minus 3 meter square kilo
Yes.
square Kelvin watt. So this is the third option. Okay, we'll move to the next question. The next question says a two fluid heat exchanger has inlet and outlet temperatures of 65 and 40 degrees Celsius for the hot fluid. So first is the cold, sorry, first is the hot fluid. THI is 65, TH naught is equal to 40. Then for cold fluid 15 and 30, TCI is 15 degrees Celsius, TC naught is 30 degrees Celsius. Determine the effectiveness of the heat exchanger. What is the effectiveness of heat exchanger? It is Q by Q max, right?
Yes. Q by Q max.
Now this Q max, it depends on, it is, I mean, it corresponds to delta T max. Okay, because this Q max is equal to how much? MCP minimum into delta T maximum. Delta T should be maximum for Q max. This is equal to this. So first we have to identify which one is the delta max. I mean, for which fluid is the delta T maximum? Is it for hot fluid? Is it for cold fluid? Can you say which one is maximum? Is it hot fluid or is it cold fluid? Just do the delta
for
T.
hot hot fluid.
Yeah. So the difference here it is coming as 25 degrees Celsius and the difference here it is coming as 15 degrees Celsius. So delta TH is greater than delta TC. Okay. So that fluid should have the MCP minimum. And what about the Q? Q anyways, it is the same. I mean MCP delta T for hot fluid is equal to MCP delta T for cold fluid. But if it is for since MCP for hot delta T is maximum for hot fluid, so MCP for hot fluid is lesser than MCP for cold fluid, right? So we can write this Q in both the ways. If we take this, Q should be MCP H.
Ma'am, how will take MCPH in this question because there is only one temperature.
Wait a minute. This delta T max is not for hot and cold, but it is for uh, maximum delta T attained in the heat exchanger. Suppose here itself, how much is the maximum delta T which can be attained? So maximum is always THI minus TC naught. So there is a very tricky thing here. The the formula for Q max is this, okay? M dot Cp, which is minimum into delta T max. But this delta T is very, I mean, you have to be very careful with this. In this equation, I mean this formula of Q max, MCP min and delta T max. This is not specific to any fluid, but this delta T max is the maximum temperature difference which can be attained in any point of the heat exchanger. Okay, you got my point. I mean, this is the heat exchanger. Cold fluid is flowing, hot fluid is flowing. Suppose hot fluid is flowing, cold fluid is flowing. There might be certain point. This is the length of the heat exchanger. It might be parallel flow, it might be counter flow, anything. But at all the points in whole throughout the length, the delta T, the temperature difference may not be the same. Okay, between delta T means the difference between the hot fluid and the cold fluid. That it may not be the same. It at some point it might become very low. It at some point it might become very high. Okay, so there might be some point where the delta T is maximum. So that happens in this. For parallel flow, it is very easy to visualize. Anyways, THI, TH naught, TC, TC naught, this is TCI. So delta T is maximum at the inlet. You know that. Okay, for for counter flow also, delta T is maximum at the inlet only. sorry, not at the inlet, you can say, because the count it is reversed in counter flow, it is reversed, the direction is reversed. So you will get here, this is the maximum. So Thi minus Tc naught, this is the maximum difference, temperature difference obtained for a heat exchanger. But now, while calculating Q, we know that MCP. So just now you have asked me, how do we understand MCP is minimum for hot or MCP is maximum for cold? How is it? Because we know that now this temperature difference MCP delta T for hot, suppose this for hot, this equal to MCP delta T for cold, right? Now this delta T, these are not the same. These are not the same as this delta T max, okay? This delta T and this delta T, they are calculated solely on the basis of, I mean, just for what? Individual fluids. This whole one is for hot fluid, this whole one is for cold fluid. Now, since these are already equal, this is due to energy balance, this is equal, okay? So delta TH is we got as 25 degrees Celsius and delta TC we got as 15. So if this is high and this is low, so obviously the corresponding MCP, this should be high, this should be low, right? Because it's energy balance. I mean, it is balanced. So like that, we came to know that MCP for hot fluid is lower than MCP for cold fluid. You got my point?
Yes, ma'am.
Yes. Now, now why this is important to understand which is minimum, which is maximum? Because which MCP is minimum, which MC is maximum? Because to find out this part of Q has two parts. One is delta T max, which I have already told you. Another one is delta MCP minimum, which is found out from here. So minimum MCP is of the hot fluid. Okay. Now this uh, effectiveness can be found out like this. So Q max is anyways MCP. So minimum MCP is hot fluid. So directly I'm writing H and delta T max. And above Q, you may write MCP delta T for hot fluid. You may write MCP delta T for cold fluid. Both the ways. But which will be beneficial for you? Because in this question, none of the mass flow rate or heat capacities are given for both hot and cold. Okay. MCP. So to cancel this out, you can think of a way to cancel this out. So we can, above also we can write for hot fluid, that is m dot Cp into, for hot fluid it is Thi minus Th naught. You got this right because we can cancel this out.
Okay, okay. It is very conceptual because this type of question will be asked in exam. So and we just think about there is a not given MCP.
Yeah. So even in gate questions also such questions, I mean, you have to
This
find.
question is very helpful for exam point of view. But previous questions already solved in assignment. This
Okay,
type of question is very good.
okay. So anyways, in class notes, yeah, okay, fine. So this delta, now you know this Thi, what remains is only this. So now I have to, I'm erasing this. So what remains is epsilon is equal to Thi minus Th naught divided by delta T max is found out by Thi minus Tc naught. So find this out. Thi is 65, Th naught is 40. Again Thi is 65 minus Tc naught is 30. So it will be 25 divided by 35. How much you get?
0.71.
Okay, so it will be the,
Option B, I think.
it is not, sorry, it is not Tc naught, it is Tci because it is 15 degree. Okay, so if the values are given, you have to find out from the values. The maximum temperature difference is from here. I mean 65 minus 30, if you do, you will get 35. But if you do 65 minus 15, you get 50, right? Sorry, I'm extremely sorry. This should be TCI. 25 by 50. So this maximum temperature, this concept was not valid for parallel, right? Because if I do TC naught, um, since TCI is much lesser than TC naught, okay, so this T max should always be THI minus TCI. I think sir has also written that, no? Yeah. Yes. I'm sorry. Maximum temperature difference can be attained only by THI minus TCI because THI is the highest temperature in all of the four temperatures. TCI is the lowest in all of the four temperatures. You got it? You got
Yes, ma'am.
what I'm trying
There
to
is
say?
only confusion between the temperature.
Yeah.
Every question calculations are very simple,
Yeah.
but temperature difference or which temperature will take at what condition. This type of conditions are hard to solve this question.
Okay. So I'm just little bit you neglect whatever I have told before. Whatever is the this is for general, okay, in all situations. THI, TH naught, TCI, TC naught for any situation, be it parallel, counter, shell and tube or anything. THI is the one which is used to heat the hot fluid. So the hot fluid will release the heat, okay? Then it will gain TH naught. And cold fluid is the one which is the fluid which is, I mean, having the low temperature and it will extract the heat from the hot fluid and it will gain a temperature of Tc naught. So this much we know that what information we get from this temperatures, that Thi is greater than Th naught because it will lose heat, and Tci is lesser than Tc naught because it will gain heat, right? So this is one thing which we get from the any system. Another thing which we get is Thi is the highest among all these temperature, that you agree, right? Thi is the highest maximum, and Tci is the lowest temperature among all four. You don't, I mean, we are not quite sure about Th naught and Tc naught, okay? But definitely Thi is the maximum highest temperature and Tci is the lowest temperature of any heat exchanger. So the maximum possible, this is theoretical, that's why. Maximum possible, I mean, this is not possible to achieve in actual heat exchanger, but theoretically you can calculate this maximum temperature. So Thi, just forget this. This is wrong. This equation is wrong. So maximum possible is Thi minus Tci. You got it, no? This is for any condition. Did you get, or you have any doubt?
Yes, yes.
Yes.
Just remember that uh, for the temperature is flow from higher hot region to cold region. This concept will be applied in this conditions.
Hmm.
It means that you say that temperature hot fluid temperature inlet temperature is greater than outlet temperature, or cold fluid uh, temperature outside is less than temperature inlet. Yes.
No,
Oh,
for cold fluid, temperature outside is higher than inlet because it is taking up the
yes,
heat.
yes, ma'am.
And flow is not from uh, higher to lower region. It is, I mean, they have specific designated tubes for them to flow. Okay, hot fluid flows in one pipe and cold fluid flows in another pipe. So while flowing, there is some exchange between the hot fluid and the cold fluid. The hot fluid releases the heat to the cold fluid, and the cold fluid takes up the heat from the hot fluid. This is the thing. Uh, you practice more, you will get it, and you can again go through the lectures also. Okay, we'll move to the next. So this is 0.5. The answer is 0.5 in this. Sorry, not this. 0.5. Ethylene glycol and water at 60 degree and 10 degree respectively enter a Shell tube heat exchanger for which total heat transfer area is 15 meters square. So it has given the entrance temperature for both, that means Tci and Thi. So which one is the hot fluid? Just by looking at the temperatures, you will get which one is the hot fluid, which one is the cold fluid. So hot fluid is ethylene glycol, and then entrance temperature is 60 degrees Celsius. Cold fluid is water, inlet temperature is 10 degrees Celsius. These enter a shell and tube heat exchanger for which the total heat transfer area is given as 15 meters square, with ethylene glycol and water flow rates of 2 and 5 kgs. So for ethylene glycol, m dot H. Ethylene glycol is the hot one. So it is 2 kg per second. And for water, 5 kg per second. The overall heat transfer coefficient is 800. So U is given as 800 watt per meter square Kelvin. Determine the fluid outside temperatures. So this is a shell and tube heat exchanger. For shell and tube heat exchanger, you have to go with that correction factor. But correction factor is not given here. They have given the effectiveness. So you have to go by, there are two ways, right? One was the LMTD method. Another one is the epsilon NTU method. So for LMTD, you require the correction factor, which is not given here. And for NTU method, you require this effectiveness NTU. And for that, this epsilon is given. So you have to go with this method, okay? Epsilon NTU method. So first step is the same thing. What they have asked to find out? They've asked to find out the outlet fluid temperatures. Okay. For all the cases, Q is must, um, and in order to find out Q, you have to find the rest. So first is what they have given. They have given the mass flow rate, and they have also given this. This is always a known quantity, okay? This no one will ask you to find out. If even if it is not given in the question, they should have provided you a book, okay? In appendix, you should be able to find out what is the CP of the fluids. You can practice this, okay? In your means you while practicing many of the questions, just without looking at this CP, even if they have given in the question also, just practice it by looking at your book, the appendix side, the specific heat for the particular solvent or the particular fluid, you should be able to find out, okay? And that should be at a particular temperature only. Since the outlet temperatures are not given, so you have to rely on this only. CP. So MCP H, you find out first. 2 into CP is 2474. How much we get? We get 4948 watt per Kelvin. And for cold fluid, it is mm, it is 5, no? 5 into 4186. This we get as 20930 watt per Kelvin. So which one is greater here? The cold fluid one is greater, okay? 20,930. For hot fluid is 4,000, only 4,948. So this is the maximum, this is the minimum. So in NTU method, you have to find a capacity ratio, a parameter, which is given by m dot Cp min divided by m dot Cp max. Okay. So m dot Cp min, you already found out which one is minimum, which one is maximum. This is the minimum, 4948 divided by 2930. This you get to be 0.236. So number of transfer you need. Okay, I have not written the formula, but in class already it is written. NTU is the number of transfer unit. This is given by UA divided by M dot CP mean. So these all are related to that only, okay? This thing, this concept, mean and maximum concept. So U is given, okay, 800. A is also given, and MCP minimum also we have calculated 4948. So 800 into 15 divided by 4948. This is equal to 2.43. So once we get this NTU, then we have this Q, which is equal to epsilon MCP minimum delta T max. So in the previous questions, all were directly Q is equal to MCP minimum into delta T max. I mean, in the previous question, there was no epsilon. So maybe they have considered effectiveness as 1, okay? But here they have given the effectiveness 0.81, 0.81 into MCP. MCP minimum we know 4948. So now it is very easy to calculate this delta T max, because this delta T max is THI minus TCI. It only depends on the inlet temperature. So inlet temperature both are given 60 and 10. So if the Q we get it as 2 into 10 power 5 watt. Now we got the Q. Now it is very easy to calculate TH naught and TC naught. So Q is equal to MCP for hot fluid, THI minus TH naught. This is also equal to MCP for cold fluid, TC naught minus TCI, right? So we equate this once to calculate TH naught, and also we equate this once to calculate TC naught. Okay, you got it right? So TH naught we get is
Yes, yes.
19.6 degrees Celsius, and TC naught also we get 19.6 degrees Celsius. So here both the outlet temperatures become same. So since both the outlet temperatures are same, after this there will be no more, I mean, heat exchange. This was of no use here. This finding out this empty NTU, it's 2.43. But it is a formula you should remember. I have not written in the that formula list. You should remember UA by MCP mean. Okay, we go to the next question. An automobile radiator may be viewed as a cross flow heat exchanger with both fluids unmixed. Water which has a flow rate of 0.05 kg per second enters the radiator at 400 Kelvin and is to leave at 330 Kelvin. So from high to low, that means it is the hot fluid. THI 400 Kelvin, TH naught 330 Kelvin. The water is cooled by air that enters at, so air is the cold fluid. PCI, it enters at 300 Kelvin, this one. And the mass flow rates are also given. For hot fluid, it is 0.05 kg per second. For cold fluid, it is 0.75 kg per second. If the overall heat transfer coefficient is 200, that means U is equal to 200 watt per meter square Kelvin. What is the required heat transfer area? Area you have to find out. So here they have given CPH, CPC, NTU they have given. So NTU method can be used here also for cross flow heat exchanger also. It is not only for shell and tube. So here same thing, you can proceed in the same way. So in the previous question we saw NTU is equal to UA by MCP mean. NTU is equal to UA MCP mean. Now your task is to find out which one is the MCP mean, whether it is for cold fluid, whether it is for hot fluid. Then you already know U. U is given this. NTU is also given 1.5. So directly you can calculate this A. This is also an easy equation. And here you will be able to use this NTU formula also. So just find out here which one is the MCP minimum MCP. Whether is it for cold, is it for hot fluid. So for hot fluid it is mass is 0.05 into CP is, it is given 4209. And for cold fluid it is 0.75. Please calculate this MCP for H. Both the values you calculate.
Hot fluid 210.45
For hot fluid
MCP
it is
minimum. Hot fluid.
two.
Water.
How much value?
210.45. 210.45.
Okay, okay, fine. And for this is, I think, greater, no? Whatever it is. 14732. So this is the minimum for hot fluid. So use that only. Directly you use. So A is equal to how much? NTU into MCP. You have already calculated MCP mean divided by U. 1.5 into 210.45 divided by U is 200. How much you get?
Option
option option B. Your voice is breaking. I think you told option B. Okay, anyways, this easy calculation, so it's option B. So any confusion in today's class?
No, ma'am. All the concepts clear. As well, confusion.
Only the
Whatever I saw the assignment questions
your
was
background
clear in
noise
this
is
session.
too much.
I'm not speaking now because my background
Okay, okay, fine.
was so.
Okay. So only the thing which I wanted to clear is for Q it was MCP mean into delta T max. This is for individual fluid, and this is considering maximum, whether maximum temperature gradient. Individual fluid means it can be either, this can be of either cold or either hot fluid. In today's class, whatever we have seen, it is mostly of hot fluid only. So it is either cold fluid or hot fluid. But this is not for individual. It is the temperature difference between the hot and the cold actually. So it is considering both the fluids, uh, temperature difference between both the fluids, you can say. Between both the fluids. So this might little bit remove the questions or some doubts if you have. So this is for, we should not mix with the fluids. Okay, this is for individual, either specifically it is for cold or it is for hot, and this we have to find out where in the heat exchanger this happens at the maximum. That is usually THI minus TCI. This only is the maximum Tmax. This is always the maximum Tmax. Okay, and in a heat exchanger there are specified tubes. Okay, they don't mix. Till now we have not studied any situation where fluids are mixing. They are flowing in individual I mean one fluid, one hot fluid in suppose in shell or in tube, suppose shell and tube in cold in tube. So they're having specific tubes to flow in, they are not getting mixed. Okay, so this is what we are considering right now. And yeah, that is the thing for today, I would say. There are more questions, but these are in this they have given more parameters, which is this is for if it is, if the shell passes more than one, like two, four, mostly they have given for two only, more than one. So n is equal to 2. That means that there are two shell passes, and f they have given. This is some correlation factor. Okay, these are some other factors. This will do in the next class. I mean, these are anyways not, I mean, not taught in the class. So this something like extra. Okay. So we'll continue with this in the next class, and I will also come up with your this view factors, and some resistances questions are also there in view factors. Those also we will do in the next class. Okay, don't miss the next class. That will be the last class of this full session. Okay.
Okay, ma'am.
So
Thank
you stay
you. Thank
from
you.
4 p.m.
Yes, ma'am. Yes, ma'am.
Okay.
I will present.
Okay, okay.
Thank you.
Yeah, thank you.